All right, guys. Let's see. That's the most exciting part of the class right there. I'm going to do a little review of some of the stuff we've done recently and then kind of like push into the next level of stuff. So, this was somebody asking a question earlier. So real quick, we're about to get into section A2, and there's a reason I skipped it, and I think I told you it's because A1 and A3 both use z-scores. A2 introduces something new, so I want to kind of work us in the direction of understanding why there needs to be something new for section A2. Somebody remind me exactly what this symbol here means.
That's the standard deviation
Of
a
population. I love it.
population.
So this is a population standard deviation. Let's get even more specific now, because I want to contrast it to this symbol.
That's the
Right, so this is the population standard deviation for how spread out. If you guys remember, this is the one. Remember, this formula for this one was this, and of course is the sample size. So in this one, I would have taken a sample, and the little subscript tells you what it is. It's the standard deviation of the sample means of groups of size n. Okay, so stay with me. So the standard deviation that they give us sigma. It's going to be population standard deviation of individuals. It's how spread out individuals are from the center. So if you picked one random person on campus and they were 60 years old, right? If you just pick one random person and they're 60, how much do you freak out about that? Like just a little tiny bit, right? Because you expect somebody to be closer to the average age, which is like 20 something. But you're not going to totally freak out. What if you took a sample of 80 people, a random sample of 80 gross month students, and their average age was 60? Do you understand? How much do you freak out now?
a lot.
More. You're like, what the hell happened? How old am I? You look in the mirror, oh my God. Do you guys follow what I'm saying? So if I take a group of people, their sample mean should be closer to the average than any individual person would be expected to be. That's why the standard deviation gets smaller for groups. So this is the population standard deviation of groups. Means of groups of size n. That's why when I ask you a question about a sample mean, I must use this, what I call the new standard deviation. It's actually called the standard deviation of the sampling distribution, which is a horrendous title. But it just means standard deviation for groups. This is for individuals. Okay.
What does it say right there, right next to of? The last word of the sentence?
Size n.
So,
Size n. So n is the sample size.
Alright,
Yeah. Like it. So I'd say like a group of size 80. I like it. I like it. Okay, nothing crazy there. Somebody remind me what this symbol means. What's this symbol?
sample?
I want somebody to just go, it's the letter S.
Sample, that is the S. Or it's a
No,
weird.
it's not sample,
It's a 5.
right? Because I already have a symbol that means like the number in the sample. You guys know what this is, right? What is this? What is S? It's exactly the same as the difference between this symbol and this symbol. What's this symbol?
Mean.
Of
Population.
population mean. This symbol is
Sample mean.
sample mean. Greek, not Greek.
So then that's
Population standard deviation,
sample standard deviation.
sample standard deviation. And more specifically, of individuals. So if I took U6, I took your ages, and I calculated the standard deviation, it would be S, your sample of my class. Every day I get a small sample of my class done. I step on tests, then I get a larger sample, which is great. I get to see people, I'm like, I can almost remember your face. I'm sorry. So, come to class, people. Okay. So I'm going to have to do the same thing. And in fact, real quick, if I did take a sample, you guys are my sample. Let's all remember how to do something. So let's actually do this for real. Everybody comfortable telling how old you are?
Yeah.
How old are you, Sabrina?
20.
20. 21. 17.
18.
18.
19.
19.
Oh my god. 18.
18. All right. I won't put me in there. Really throw us off. A little bit of an outlier.
25.
Can you guys take a minute? If you need to borrow a calculator, come on up here. I want you to put these values into list 1 and calculate the mean and the standard deviation. So if you need a calculator, I've got some. This will be a good little review of how the hell to do this. Sure it turns on. Don't give me that. There we go, sweet. Full battery. Oh, neat. Wow. Again, you saved yourself. I don't want to have to throw you out, man. That'd be embarrassing. For
Actually,
both of us.
we actually had to throw someone out on Saturday.
A what?
We had a piece of my job as a bouncer. Some
Yeah.
guy was bumping into people. I told him, you need to leave. He's like, make me. He pushes me. I was like, okay. And I sucker punched the dude in the face.
Sam, okay.
And my manager grabbed him and threw him out.
I'm glad. It sounds like he needed to be thrown out.
Yeah, even before he even went inside the club, we didn't even allow him to come in because he was drunk already. We told him he needed to sober up.
Alright, let's get these data points in here.
Yes.
Do not miss the club scene too much. Catch up to you guys. Go ahead and get them in there and try to calculate the mean and the standard deviation. There you go.
It's trying to do the same.
Huh?
I couldn't do it.
Ryan, we're putting these in the calculator to calculate the mean and standard deviation. A little review. Come on.
I get a calculator.
Yeah, what you got? Got your calculator. That is a very valuable let's do that. Alright. 20, 21, 17, 18, 19, 18. Okay. So where do I go to calculate this, the mean and the standard deviation? Second.
Second step.
Not second step, just step.
Oh, yeah.
And then where? Where do I go?
Two.
No. Go to calculate, number 1. And then that, so make sure it's list 1, the frequency list. If you have an older calculator and just says 1 more stats, you just hit enter, it defaults to list 1.
Just on mine says L5. I don't know how to get to the back.
Just hit clear and then put L1.
How do we put the L? Wait,
Second one, see above 1 it says L1. Look at the 1
about
there.
there.
So hit second, because you have to shift.
Oh,
Hit second, the blue button.
this one.
Yeah, that's like your shift key. 1.
Oh, okay. Sweet. And the same
Make
thing
sure
for
the
the bottom.
frequency list is clear, and then go down and calculate.
So we do L1 again for this one?
No. Make sure it's clear. We don't have a frequency list. Yeah.
And then enter for calculate.
Enter for calculate. All right, guys. Tell me out. What's the sample mean? I kind of gave it away right there. What's the mean?
18.
Yeah, 18.83. So the average age in here, before Ryan came in, Ryan, you're not a part of it, was 18.8. How old are you, Ryan? 18, all right. You would have kept it pretty much run down a little bit. What's the standard deviation? Yeah. The 6 numbers we put in there, are they a population or a sample? They're a sample. Right? Therefore, we got to pick S. I love it. I love this thing. Okay. Over does it. So when we put data in, anytime we put data in and we have the calculator do things for us, we still have to know what to look for. The calculator is going to give us both of these because the calculator is stupid. We're smart. We're humans. Calculator is a piece of thing. So it just gives me both. It says, hey, human, you know if this is a sample or a population. You take the right one. Is everybody with me? A little bit? So this is the standard deviation for this sample. It's how spread out the individuals are in the sample. If I asked you a question about the sample mean, I would still have to create a new standard deviation. I would still have to do this, the same way I have to do this. People think this somehow makes it a sample standard. No, it's a standard deviation of all the sample means. This would be a standard deviation of all the sample means I could get from a sample. I still have to do this. Okay, maybe. So the only difference between sigma and S is this is talking about a population, this is talking about a sample. So everything I have to do to sigma in certain situations, I also have to do to S the same way. Okay, real quick. Oh, sorry. What's up?
I feel like a fool because I'm not getting that. It's just off by a little bit.
Oh, how much?
Like very little bit. Here. Like double, triple, million, billion.
Million, billion. That's a lot. That's interesting. Oh, he did a frequency list of L1.
That's supposed to be.
We don't have a frequency list. The frequency list would be
Gotcha.
if I had, sort of like when we did histograms, we'd have a data point and then next to it we had the relative frequency.
Oh, okay. So
We don't have a relative frequency.
Yes, I was saying that there's 20, 21, 20.
Yes,
21,
which is why it came so close, because it's almost the same
Yeah.
number anyway. Yes, okay.
That makes sense.
Okay. Now, what do you think the actual standard deviation of ages would be if I took everybody enrolled in the class, which is more than what you see here, right? If we took everybody, would it be this?
No.
If I calculated this for the whole class, do you think it would be this?
No, I think it'd be,
I'd put money at not being this, yes?
I think it'd be close.
You're just a sample. In fact, Ryan's like, I didn't get included, right? So you're just a sample. If I include Ryan's age, let's see what happens. You said you're 18?
Yes.
All right, let's see. Bum. Yeah, one more stats. So it becomes, it's different, 1.38, right? Went down a little bit. Why does it make sense it went down a little bit? Because the average is about 18, and you are 18. So I put one more data point that is actually not far away from the mean, so of course the number that measures the average distance from the mean went down a little bit. Because you're right on the mean, just about. Is everybody with me a little tiny bit? A little bit? Okay, so listen. So somebody else just came in, right? So I got more people than are here currently. If I took all of them, what is our best guess for this? At the moment, what's the only thing we got? What's our best guess for what this really would be if I took everybody that's enrolled in the class and calculated the standard deviation of their ages? What's our best guess?
The sample.
Yeah, the sample standard deviation. In fact, now it's gotten a little bit better because we have one more person in there, right? backing up a little bit. Because I really want this to make sense, obviously. If we don't know sigma, our best guess is S. Inherently, that means that S will almost definitely be wrong. And when I say wrong, I mean it's not exactly the same as what the actual full standard deviation is. All right, so when we create a confidence interval, what we've done so far is somehow magically we've always known this. And there are situations where we will know that. But the whole idea of confidence intervals is we go into a situation and we do not know what the average is. So for example, if I went to some random little island, do I know what the average number of species is on that island? No idea. Do I know what the standard deviation of things amongst the species? No, I have no idea. So I'm only going to be able to get X bar and S. I'm not going to have this. It's a complete unknown. You find another planet, right? What's the average temperature across the planet? We don't know. We're going to take samples. We're going to do our best. We don't know what all the temperatures are. Okay, so everybody with me so far? So if I know this, that kicks a lot of ass. If I know this for sure, I'm as sure as I can be about everything. If we are forced to use S instead, that is just an approximation. Just an approximation. So help me out. If I take a sample mean and I want to be 95% confident I catch the real mean, wouldn't I just go 2 kind of steps up and down, right? That's what I see here. I would go 2 of these, not 2, Jeff. I would go this many steps up and down. For 95%, it's almost 2. It's the 1.96, right? You guys semi with me? Okay. What do you think will happen if I still want to be 95% confident that I catch the real mean, but I have to use frickin' S? I have to use an estimate of the standard deviation. What should I do? Should my interval stay the same size? Should it get bigger? Should it get smaller? If I want to be the same amount confident, but I'm not even sure about the freaking standard deviation I'm using, should my interval get bigger or smaller?
Bigger, probably.
Bigger. So if there's an escaped convict out in a neighborhood and you have no idea how fast he runs, how big of a search area should you do? A bigger search area. If you knew that this person had a major injury to a leg, you might not need as big of a search area. You're more certain about how spread out he might have gotten. Yes? Does that make any sense? That's completely made that up on the fly, so hopefully that makes sense. Okay, maybe. Okay, so I really want this to make sense. What we do, I'm going to have to, I still have this. Everything's the same, right? X bar, plus or minus, leaving this empty for now. Standard deviation by the square root of n. Those parts don't change. But if I just use a z-score here, I'm going to go out the same amount. I've got to go out further. If there is something we are not sure about in what we're looking at, I have got to catch more stuff to cover my ass for the fact that there's something I don't know. I don't know what the real standard deviation is, so I've got to catch more shit. I got to catch more stuff. Does that make sense? This is an actual physical problem. If I have no idea where the fish is in the lake, I'm going to throw a bigger net out just to be more certain, at least that confident that I caught that fish. So, what we do, we don't use z-scores. We use something that is always a little bigger than a z-score, so that makes it go further out. We use something called t-scores. And I can almost read your mind. You're like, oh, come on. So it's going to be a new table. I'm going to give it to you. We're going to talk about it. What do you think? Okay, I really want this to make sense. If I took a sample of size 2 from a population and I calculate the standard deviation, do you feel pretty good about that standard deviation compared to like the real population standard deviation? So let's say we take a sample of size 2, a sample of size 2, and we calculate an S from 2 things. How close do you think that's going to be to sigma? The actual full population standard deviation.
Definitely not.
No, I put money on being way far off. Yes? I really want this to make sense. Maybe? In fact, if I pick 2 people from this classroom, couldn't I pick 2 18-year-olds? Right? Aren't there 2 18-year-olds in here? Yes. What would the standard deviation be if my data points were 18, 18? 0. They get 0 away from the mean. They are both equal to the mean. Is that different from what we got? Shit, yes, it's very different from that. In fact, and that is still even different from the actual full standard deviation. Okay. If this guy's purpose is to always be a little bigger than z-score to cover our ass because we don't know the real standard deviation, this should kind of change how big it is based on how big our sample is. If we took a large sample, if we took 2,000, let's say 20,000 people, are you more confident that this is close to this compared to 2? Does that make sense? If I take 20,000 people and calculate a standard deviation, I'm feeling pretty good that that's close to the actual population standard deviation. If I take, let's make this a little more reasonable. If I take 20 people, these could be really, really different. If I take 20,000, now I should be really getting close. I feel more confident in what I'm getting. So as my sample size goes up, this should get smaller and smaller and start to get closer to this. So what's this guy's purpose? This guy's purpose, if I have a confidence interval here, this guy would push this out. I'll catch more, I'll catch more stuff because I'm less certain about how spread out things are. I need to catch more stuff to make up for the fact that I don't know the real standard deviation. But if I take a larger and larger sample, this guy should have to go less and less further out, less and less further out. Does that make sense? The bigger the sample we take, the more certain we are about anything we calculate from that sample. You guys knew that day 1 of this class. So, what should be true if I take a very large sample? If I take a very large sample, almost as big as the population, then I'm really sure that these are close to each other. Then I could just use a z-score. I don't need something to cover my ass. If I take a really large sample, then I can just go ahead and use a z-score because I don't need a bigger thing to cover my ass because now I feel pretty good about what we find. So, that's one thing, right? And by the way, just a little side note, the person who invented this idea worked for Guinness Brewery. And he had to sign an agreement when he worked with them that said any research he did was owned by the company. He did some research and he kind of came up with this idea because he was sampling Guinness stuff and he was coming up with some data and he was trying to create a new way to analyze it and he came up with this idea. So he submitted the idea under the pseudonym Student. So you will sometimes see this referred to as Student's T distribution. It's actually William Gossett, who worked at a Guinness brewery who just wanted to protect his stuff from the company. And I love it. You guys are all like, I'm as interested in that as everything else you said so far. Okay, I understand. So, one thing is the main job of a t-score is when I only know S, the t pushes the interval out of it to cover my ass for not knowing something, right? Does that make sense on its surface? If there's something I'm not sure about, I'm gonna kind of like push it out. So if I knew that tomorrow there was gonna be a package delivered at my house, and I'm like, people's been stealing my packages, I'm like, I gotta make sure I'm home. And you have no idea at all when it's gonna be there. You're gonna push out the interval of time that you're gonna make sure you're home. Does that make sense? If you know really certain, if you're really certain it's gonna arrive between 12 and 2, then you're gonna kind of stay home from 11 to 3 maybe. You're gonna push that interval in. But if you have no idea about the spread of when it could show up, you're gonna kind of widen the interval of time that you're gonna be home. Okay, maybe. I don't know if anybody's ever had your stuff stolen from your porch, I don't know. No, thankfully not. I'm like around the corner behind this other house. I'm in a great place. All right. Okay. So that's one thing. That is one thing. So what's a T-score's job? I have to use a T-score when I don't know sigma. I only know S. And the really cool thing is, you're going to write this formula down in your formula sheet. You're going to write that formula down in your formula sheet. And this tells you exactly when to use T. I use T when I know S. I use Z when I know sigma. Okay, I like it. So far, so good. Or decent? Okay. So the next kind of idea that goes with this. It's something I've been neglecting to come back to. Two things. Help me out. If I want to create a 90% confidence interval, what's the total area that's in the tails? In fact, can you guys see easily what part of this would be called the tails? Right? So what's the total area in the tails? 10%. 10%. Math people, we don't like too many words, right? So we take this area in the tails, and I'll say it like this, tail or tails. Because there could be a one-tail situation, we'll see that in the next section. But confidence intervals always make two tails. Does that make sense? You chop off the middle, you're going to make two tails. The symbol we get for this is the Greek letter A, which is alpha. And the great thing about that is it looks like a little fish. So a fish has got tail, right? So then you can think fishy dude with tail, that's the area in the tail or tails. So this symbol, I think, has come up in the homework somewhere. And I always forget just to tell you what the hell this symbol means. But that's what it means. The area in the tails. So if I wanted to make a 98% confidence interval, what's alpha?
2%.
Yeah, 0.02, right? Do you guys see that? That's all it is. Alpha is just the area in the tail or the tails. And confidence intervals always makes two tails. Yeah, I like it. I like it. Now, the other thing. So if I wanted to make a 98% confidence interval, alpha is 0.02. Beautiful. Okay. Now, last piece we need. So we've got, let me count, we have this formula we've done before. We've got this new formula for when I don't know the actual standard deviation. We got this idea of alpha. Now there's one more thing we need. Let me see if you guys are cool with this. I have 3 numbers in my head right now, and they average to be 10. Can anyone tell me any of the specific numbers? No. Ain't no damn way, correct? So I've got 3 numbers in my head. And they average to be 10. You don't currently have an idea. They could each be 10. Or they could be different. They just have to average to be 10, yes? You do know something, though. How do I calculate the average of 3 numbers? What would I do?
Divided by 3.
Divide what by 3?
Divide the average by, or the sum by 3.
Yeah, so I'd add them all up, divide by 3. What do you divide by 3 to get 10? 30. So you don't know what any individual number is, but you do know they have to add to be 30. So if you're going to make a list of numbers that averages to be 10, does the first number have to be something specific? It could be whatever the hell. Somebody give me a number.
17.
17, okay. Second number, does it have to be anything specific? No. Somebody else give me a number. 3? 3, over there. Last number, can it be whatever the shit it wants to be?
No.
Hell no. What have I got so far?
20.
20 total, and I need 30 total, so what's the last one gotta be? 10. That averages to be 10, correct? And you could keep doing it. So, let me say this very strange thing. Let me see if you guys get this. How much freedom did we just have?
2 out of 3.
I had 2. So my degrees of freedom. That's a very strange way to say this, but you understand how that refers to how much you could just completely make up. It's that last dude that goes, okay, wait a minute. We got to make sure we get 30. Right? You guys are with me so far? A little bit? Okay. So this is just a phrase that us weird-ass stats people use for this idea. So we normally use BF. What's the N here?
The N is
3. So the degrees of freedom seems to be 3 minus 1. So the degrees of freedom might be N minus 1. In fact, if I had 10 numbers that average to be 10, the first 9 can be whatever the hell you want to, and the last one has to be the thing that makes them add to be the right number. You always have N minus 1 things that you can just play around with. Does that make sense? Does it make sense? Yes? Okay. I really want you to understand why we use this phrase. Well, you don't understand why we use exactly that phrase. I don't blame you. It's just a phrase we use. So, let me give you this. Oh, before I give you this, let's do one thing. Can somebody please look up for me, if I was using a z-score, meaning I know sigma, can any of you figure out what is the z-score for 95% confidence? 1.96, I love it. Okay. Let's keep that in mind. All right, so really sorry. By the way, just so you know, we have one more chart like this for the semester, right? Just so you know, every week we're not going to get a brand new table. Let's see how the hell to read this thing. So, the way to read this is to zoom in. So look real quick. Do you see the top 2 rows? That says area in 1 or 2 tails, right? Which column are we going to look at for 95% confidence? What's the area in 2 tails for 95% confidence? Yeah. 0.05, right? So I'm going to look right there. That means 95% confidence interval. Because a 95% confidence interval is going to have 5% outside. So if 98% would be 0.02. What about 97%? Can't use this table. So this table is only good for 99, 98, 95, 90, 80.
So we write that down or
No,
Okay.
yeah. So again, this is just like the z-score chart. Don't put any notes on this chart. You can put your name on it if you want to. But don't put any notes on this. You're going to be using this for tests. All right, so let's say I take a sample of, so now let's say the same situation, I want a 95% confidence interval, but I only know S. I don't know sigma. which means I'm gonna have to use a t-score, right? T's go with S's. And let's say I take a sample of size 41. Let's see how to read this thing. 95% confidence, I know it's the middle column. Where do I stop for 41? What's the degrees of freedom if the sample size is 41? What's the degrees of freedom? 40. Off the chart. So we go down to 40. 40. And then 95% is the middle column. So we get a t-score of 2.021. So again, what's the t-score's job? Is to push the confidence interval out a little bit because there's something we don't know that we should know. We don't know the real standard deviation. So it's going to make our confidence interval, it's going to make us have to deliver the confidence intervals a little bit bigger than we wanted. We kind of get penalized because there's something we don't know. That's another reason why I love statistics. It's like, okay, you don't know this shit, we're going to penalize you because you don't know something. There's something you don't know. What was the actual z-score? If I could use a z-score, it was 1.96, yes? What if my sample size was large, and they literally put large? What score would I use? 1.96. So that's exactly what I said. When my sample is large enough, the t-score will become a z-score. Because the only purpose a t-score exists is to push my confidence interval out if we're not sure about the standard deviation that we're using. If I take a huge freaking sample, then I'm pretty confident my S is close to my sigma. I don't need t-scores help anymore. I don't need it to push my confidence interval out. In fact, look at all these other ones. 1.96, 1.645, does that sound familiar? Maybe?
Yeah,
That's for
90%.
90%. This one maybe 2.33, I think we've done a 98%. 2.575, this is actually a little bit better, 2.576. That was for a 99% confidence interval. Okay, so.
This is another, like, it's kind of like, is this another version of the z-score?
Yes, you just missed a really crucial part of the lecture, so make sure you watch the video. Okay, so. I got, believe it or not, I've got a hand. And what I want you to do, let me see. I want you just to do number 1, part A, B, C. Right, this is just testing to see if you can read the chart. Oh, again, turn. There's one side that's got a bunch of data on it. I want us to do the other side. Sorry, I should really give it to you like that. That would be good. One side's got a crazy big ass amount of data. Don't look at that side.
Oh, thank you.
Anytime. So take a minute and do the top 3 problems here. These guys here.
I really thought it was like 6.99% confidence.
Oh, sorry. Yeah.
Like 101.
Yeah, you want to be 7% confident. That sounds
Okay, that makes sense.
sounds close to right for some situations for me. 7% confident in this here. You guys comfortable in here? Does it feel okay in terms of temperature?
Yeah, that feels good.
This freaking AC is weird, so I have to keep on top of it. Okay. All right, let me look at this first one. You guys, can somebody tell me degrees of freedom for the very first problem?
5.
Yeah, so it's always n minus 1. So degrees of freedom is 5. I want to be 99% confident. So somebody else tell me which column we're going to look at. If I'm 99% confident, how much area is in the two tails? If I'm 99% in the middle, how much is outside? Yeah, 1%, 0.01. So really, is everybody with me on that? I mean, they're not gonna tell you, they could have, but they're not going to. They're not gonna tell you 0.99 for 99% confidence. They're gonna give you the area and the tail. Why are they gonna do that? We'll see in the next section. This idea of area and the tail is kind of huge. So this is a 99% confidence interval because 99% leaves 1% out in the two tails. And then I'm gonna stop at 5. You guys with me? Do you guys understand? That's pretty huge compared to any z-score we've used, right?
Can you show that again? I didn't.
Yes. All right. So for part A, degrees of freedom is always n minus 1. So that's n equals 6, so degrees of freedom is 5, so I'm going to stop here, right?
Okay.
Confidence interval 99%. What's outside? And if it's a 99% confidence interval, what's outside? How much? 99% inside, what percent outside? 100% total. So if 99% of the people were inside of a room, what percentage are outside? 1%. 1%.
Oh, that makes more sense.
In two tails, yeah. So then you start here and you stop at 5. If you go all the way to the bottom, you always get a z-score. So on the t-score chart, z-scores live. They're at the bottom. In fact, the t-score chart kicks even more ass than the little baby chart. If I wanted to make a 98% confidence interval and I need a z-score, I would just go to 2% and I would go all the way to the bottom. So on this chart, if I stop, I get a t-score. If I go all the way to the bottom, I get a z-score. That's kind of nice. Okay. All right. So the t-score we got was 4.032, is that right? All right, try to do part B and part C. Part C is going to be a little tricky. Should have asked one more question, and that would have been good. What's the degrees of freedom for part B? 100 billion dollars. What's the alpha? That's what I should have also asked. What's alpha?
0.1.
0.1. Pretty guess. So I look at the column of 0.1. Be careful, not 0.01, right? It's 0.1, and I want to stop at 100. Whee! So I get 1660. So remember what the funny thing is, if you're pretty cool about using this formula, if you're pretty good with the section where we use this formula, you have to be good with this. It's just, instead of looking at the z-score chart, I look at the t-score chart. Everything else mechanically is the same. It's all the same calculations, but the number that I put in this spot has to be different because there is a part of it that I don't know the real number. I just have an estimate. So I need this guy to push me out a little bit. Now what's weird about part C? What's the degrees of freedom officially? 92. Is there 92 on our chart? No. So what you always do is you always be more conservative. More conservative means penalize yourself more. So take this down to the next lower thing that's actually on the chart. So I'm going to go, what's my alpha in this case?
0.1. It's 0.08, but you make it 0.1.
No?
3.
0.2.
Oh,
No,
it's
two.
confidence. Never mind. Bye bye.
Yeah. Okay. 98% confidence, 2% outside, yes?
Yeah, that's my bad.
Alpha is the area in the tails. 98% inside, 2% outside in the tails. By the way, if I had 98% confidence interval, 2% out in the tails, how much is in one tail? 1%. So either way you freaking look at it, if like a 2% for two tails or a 1% for one tail, it's the same column. I really want that to make sense. So, if I have a, holy crap, 98% confidence level, there is 2% outside total, meaning that there's 0.01 in each. But either way you look at it, you get in the same 1% in one tail, 2% in two tails. You get in the same column. And then I'm going to stop at 90 now. So 2.368.
Can you extrapolate between points?
You could. Same way you could with the z-scores. Yeah. By the way, look how little it's changing down here. So look how crazy it is. Look, what does the degree of freedom of 1 mean?
It means if you have 2 data
You only have 2 data points. How certain will you be about anything you calculate from just a sample of 2? Not.
at all.
Look at the t-score for 99% confidence with a degree of freedom of 1. 63. You basically, if you take a sample of size 2, stats just says screw you, dude. Go weigh the shit out of that. You take some more sample. The minute you take 3, look at how that just jumps. Now you're a lot more certain. And of course, as you get a larger sample, the t-scores approach the z-score because you're becoming more and more certain about the standard deviation you're getting. This makes complete conceptual sense as to why it's going down and down and down, and then it eventually becomes a z-score. Now, the question I'm surprised nobody asked yet is what the shit does large mean, right? That is absolutely amazing that it just says large. But the reason that's fine is because it depends on the situation. What's large to one person might be large, not large to another person. So it depends on the situation. So it's just leaving it up to your interpretation. But look how close 2,000 is already. Right? So generally, anything above 2,000, you should probably go ahead and be able to use a z-score. Does that make any sense? It just depends on how precise you need to be. If you really need to be precise, there's a formula to calculate the t-score. Of course there is. This is just all the answers somebody had. So you could actually get it. If you had a sample size of 2,800 and you want to know exactly what the t-score is, you got a formula for that. That thankfully we're not going to do. We're just going to use numbers. Yay. Okay, so before I unleash you on the second part, can you guys remind me? Can somebody tell me? Yes, I'm sorry.
I have maybe a weird question. How do you get the numbers on these tables?
I don't know if they put the formula in the book. I'm almost certain they didn't. But if you remind me, I can bring the formula with me.
Okay.
Because of course there's a formula, right? I'm pretty certain they would not have put it in here, but yeah. So if you remind me, I can bring the formula if you want to see it in its full glory. All right. Oh, it's up there. So somebody remind me. It just said, why were t-scores invented? Not because some guy got drunk on Guinness, but I love that answer.
When you don't know the true standard deviation.
Yeah, when I don't know sigma, I only know s. That's why they were invented. So, these 4 problems, when am I going to have to use a t-score?
When you have S.
When you only have s, not sigma. When can I use a z-score if I know sigma? Now listen, there are some problems. This is huge. There are some problems in the homework. They give you both sigma and s. Which one do you use? Use freaking sigma, right? That's the real number. So why do they give you both? Because in reality, anytime I take a sample, I can calculate s. I use that if I don't have a clue what sigma is. I don't use that freaking s if I do know what sigma is. Does that make sense? I'm going to use the real thing, not my estimate, if I have it. We normally don't have it. One line. One more thing. What else has to be true? What has to be true to be able to use z-scores for something?
It has to be a normal.
Normal distribution, right? So for means, what's got to be true? N has to be bigger than, no, that's for percentages. 30. I think is what you said.
That's what I said.
So look at number 1. or part A? Is n big enough?
No,
But why is that not a problem?
because it's normal.
Because they already tell me it's normal. Read through the rest. Do I use a t or a z?
Z.
What tells me I use a z-score?
Sigma.
The fact that I know sigma, yes. So on this first problem, you say use a z-score, and then I want you to find it. What's the right z-score? So go ahead and do all four of these. There's only one of these, I think, if I remember correctly,
Yeah.
that you can't do. The answer is can't do. So try to do this fourth. So everybody should be writing unless you've already done it. So you are, just to remind you guys, if I were you, I would be using the t-score chart very frequently to find my z-scores, because they live at the bottom of the chart, right?
You can also still use
You can still use the old, yeah, totally, you can use either one. Let me catch up to you guys, so just really, you have to know going in, I need a z-score, which means I am not gonna stop anywhere. So don't stop at 21, that doesn't make any sense. I want a z-score, I know I want a z-score. So, what's alpha gonna be for this?
0.1.
0.1, 11. So two tails, 0.1, and I go all the way to the bottom, 1.645. Is that what you got, Sophia? You do it the
Old fashioned.
old-fashioned way? Exactly, that's funny, that's exactly what I was about to say. You got the same thing?
Yeah.
Okay, 11. The old-fashioned. All right, keep going. Do the other three. Oh. In order to use Z or T, you need to have a normal distribution. So either it says it's normal, or the sample size saves us, right? One of those two. In order to use Z or T, T-scores are just like Z-scores that have been beefed up, so they have the same needs to be used. Part B, is it Z or T? Why is it a T-score? We only know S, we don't know sigma. Plus, what else? Population is not normal. Oh shit. But, yeah, N is greater than 30. So we want to use a T-score. So what do we need to be able to look up the right T-score? I have to know the degrees of freedom. What's that going to be?
38.
Yeah, one less than the sample size. Somebody else tell me what alpha is.
0.02.
0.02. So now we know everything we need. So again, when you use this chart, if you stop, you get a T-score. If you go all the way to the bottom, you get a Z-score. So alpha is 0.02. Degrees of freedom is 38. So I get 2.429. Is that what you guys got?
Yeah.
Oh shit. It's probably better you can see what's going on. What do you guys think about part C? I know sigma, don't I?
Sample size is 4.
Ah,
It's not.
sample size is not big enough, and they don't tell me the population is normal.
So it's
So
also-
in statistics 1, which is what we're all in, can we do anything?
No.
Nope. Statistics 2, we could do some shit, but no, here we can't do anything. A little tease, and of course we don't teach stats 2 here, so I'm sorry.
We don't. That's weird.
I know. I'm gonna try to create a stats 2 course maybe and put it in, but I don't know if it's gonna go anywhere. Can't be done. And you're all like, great, I'll avoid that like the plague, Jeff. Damn.
Put as many of those on the test as possible.
Yes, so that's about 1. Okay. Does that make sense, guys? I mean, anything related to z-scores, I need to know the population, no, the distribution I'm working with is normal. So either the population is normal or the sample size is big enough. So part D, it's like an overachiever, right? So go ahead and do part D if you haven't done that yet. I kind of gave it away just right now, which one you have to use. Or that this can be done, I should say.
I was gonna say.
Yeah, this can be done. So the very first thing you look for in a problem is, do I know it's normal? Does it say it's normal, or does the sample size save me if it doesn't say, right? So this one is double good. It says it's normal and the sample size was big enough just in case. What part of this problem, somebody who I haven't heard from yet, can somebody I haven't heard from yet tell me, what part of this problem tells me if it's gonna be a Z or a T? Anybody? Why were T-scores invented? For when I only know what? Say again? The sample standard deviation. So which standard deviation do we know? Sample standard deviation. So therefore, I have to use T-score. So it's, if the population is normal, either they say it or N is big enough, I then just look, which standard deviation do I know? If I only know S, T-scores. If I also know sigma, or if I only know sigma, Z-scores. So in this case, I have to use T to cover my ass, because I don't know what the hell sigma is. Sigma unknown, T. So what's alpha in this problem?
0.01.
0.01, 99% confidence. What's the degrees of freedom? 60. Degrees of freedom. So if I go to 0.01 and I stop at 60, oh yeah, I get what I love. It's 2660. 2660. Earlier we got 1660. It's kind of a nice little thing. All right. So now I'm going to finally sort of shut up and let you guys do a complete problem. We did just earlier, I reminded you how to do all this stuff in your calculator. So I want you to calculate X bar, and I'll give this away, S, right? Because this is a sample. Will you be able to use Z or T? N is only 7, yeah?
Yeah. But it's normal.
Good. But it tells me it's not okay. So try to do this problem, and you've got the formula. Let me write it really freaking big up here. It's either going to be this, or it's going to be this. Any brave souls out there that can tell me what they got for the mean?
I got 78.
78.26.
Yeah, I got it.
Sweet.
No, wait, 70.
I got 78.286, right?
286. I might have just put it in wrong.
I got 285.
2857, blah, blah, blah.
Yeah.
Surrounded to.
No, you rounded up, yeah.
Yeah. Okay, good. Sounds good. Let me show you what I got here. So it's 78.286, we'll say. And the standard deviation, what's the standard deviation?
15 points.
Good. This is just a sample, so we gotta use S, 15.724. I always get somebody who tells me, but Jeff, man, I use Z-scores because my calculator told me what sigma was. Again, calculator dumb. It's gonna give both because it has no idea if the numbers we put in are a population or a sample. So we're the humans, we created the freaking calculator. It's just telling you, use whatever you need, human. So it just gives me both. Maybe, let me come back over there. So we got X bar. We got X bar, we got S. Am I gonna use T or Z?
See,
Why?
it's the sample.
Okay, two things. Only know S and
It's
norm. Because it says so.
because it tells me. Trust it.
You can trust me. Okay. So now we got everything we need. If you haven't done it yet, go ahead and try to calculate the confidence interval, and then I'll catch up with you in a minute. Oh, that's for part B. Let's see. I don't need to slam it in there. Get out of there. Well, we don't quite have everything. You gotta look up the T-score, but that'll be part of what you do. Make sure everybody's on the right track. What's the degrees of freedom?
77.
It is 6.
6. Okay. N minus 1, right? So degrees of freedom is 6. So be careful, it's N minus 1. It always relates to the sample size.
That's fine. I messed up.
What's alpha in this case?
102.
Good, 98% confidence, so I have 2% out in the tails. And that's all you need to know to figure out what the T-score is. So if I go to 0.02, and I stop at 6, 3.143. So now all the same work. So the only new thing, the only difference between the problems you're doing in section 8.1 and the problems in 8.2 is I get the score that goes here, I get it from a different chart. That's it. So now I'll still do the error first. Let's see. Everybody got the error?
18.6.
Okay, let me see what I got. See if I can do this. No, you can't do it, John. Divided by square root of 7. Yeah, 18.679. So then you have to do 78.286 minus 18.679 and 78.2786, sorry, plus 18.679. Crazy. So from 59.6 up to 96.97. Okay, that's pretty pathetic. So from a sample of 7 students.
We're not very confident.
Exactly. Well, we're 98% confident. We're pretty confident,
Well,
but
like,
in
there's a
order
lot.
to be that confident, we have to actually go down to F to A. So it's like, what's the actual average? Somewhere between an A and an F. It's like, thanks for that. Really? That's useful. Right? The only thing I can say for sure is that it's not an A plus. And even that, I'm 2% chance that I'm wrong. Why was this interval? Do you guys agree with me that that's a freaking wide interval, especially considering we're talking about grades? So that does capture from F up to A, correct? Why is that such a wide freaking interval?
Because we want to be 98% confident and we have a small sample.
We had a very small sample size. So to be 98% confident, we had to go out a crazy amount. Now, what if what if these were the same, but they came from a sample of 101 grades?
You'd be very close.
2 things would have changed.
Your
If the sample size was 101, can anyone tell me? The obvious first change would have been there, yes? It wouldn't be 7, it'd be 101. Yes? And so I'm dividing by more, so this would get smaller, wouldn't it?
Heat.
What else would change? Obviously, n would be 101, not 7. What else that we calculated up here came from the sample size of 7? That would change now. Where'd this come from?
that is the t-square.
That came from the degrees of freedom, right?
Yeah.
So real quick, let's just do this just for fun, because I can tell you guys love this shit. So let's do a little bit extra. Just for fun. So what if instead n had been 101? So the degrees of freedom would have been 100. Alpha is still 0.02. I still want a 98% confidence interval. Somebody help me out. Look up the t-score for this situation. 0.02 alpha. Degrees of freedom 100.
2.364.
Yeah. So if I go to 0.02, stop at 100, 2.364. I love it. So then my formula would have been just about the same as this, but it would have been 78.286 plus or minus 2.364 times 15.724 divided by the square root of 101. So one kind of minor mistake people make is they'll put 100 in there instead of 101. The formula needs n in there. Right? So you only use the degree of freedom once to find the t-score. Does that make sense? It's a really easy mistake to make because your brain is just like numbers. So, okay, maybe. So let's see, what would that error be now? Let's see if this is a more reasonable confidence interval. 2.364 times. Yeah, we get 78.286, give or take 3.699. Much better error than 18 point something. So now our interval would go, what would it go, Jeff? Let's see, 3.699 plus, so we go from 74.587 up to 81.985. So much more reasonable. So now I could say the actual average is somewhere from a C to a B minus. That is much better than somewhere between an A and an F. It's like, I knew that before I even asked you to do anything. Thanks. But then I would be like, well, you only gave me 7 scores. What do you want me to do? So if they gave me 101 grades, then I could give them a nice, clearer picture of what's probably true. From what was done here, could the average grade, from what we see here, is this evidence that the actual average grade is less than a B plus? Is this evidence that the actual average grade is less than a B plus? Yeah, because what's a B plus in my class? What's a B plus? Do you guys know? 88. Good try. I know it. So in my class, a B plus is an 88. So this is evidence. Why is it not proof that the actual average is not a B plus?
Because you have a 98% confidence interval.
Yeah, so there's a 2% chance this interval does not catch the real average. So there's a 2% chance that we're wrong here. Do you guys see that? So that's, again, why do I like stats so much? Because it's the most honest math. It says, this is what it feels like. You know, that's what we can do in life. In life, we don't know for sure anything, just about. Right? So statistics is like, okay, I can give you an idea, but, you know, that's all I can do. Right? Okay, maybe. In order for statistics to be absolutely sure about what it's saying, we'd have to feed it the whole population. And how often do we have an entire population to work with? Almost never. We almost always have samples, right? That's what a lot of things are built on. Why do we only do samples? Because normally a population is either way too large or way too difficult to get around to everybody or whatever. Maybe. All right, let me see. This is going to be exciting. Look on the other side. This is an actual, now to be really straightforward and honest, I collected this, it says the last several semesters. That was true probably 6 years ago. So 6 years ago, I took data from the last several semesters, average grades up to this certain point in the class, and this is what I got. And I just put it all up here, right? Everybody follow. This is real stuff. I didn't just make this shit up. Let's see how far we can get with this today. Can anyone tell me a method that would not get me a truly random sample? We need a truly random sample of grades. So here's what one person can somebody tell me what's a way you can make sure that you don't get a random sample of grades?
Pick 6 in a row.
Well, that actually that's not the best, but it's not a guarantee you don't get like a really good random sample.
Pick a bunch of big ones.
Good, yeah, pick a bunch of big ones. That's a definite way. Go ahead.
Oh, since I ran generator or something.
Oh, well, that's a way to make sure you do.
Oh.
I want to know how you make sure you don't. Here's a good one. What about picking all the ones that end in 0? I had somebody do that one semester. Do you guys understand that that won't be a truly random sample? Yes? That will be skewed. So what is a way you could, in this class right now, get a random sample of grades? Because that's what I need you to do. I need you to randomly sample 20 grades. What's one way you could do that?
Just point somewhere and pick those.
Okay, beautiful. I got, Sophia says, start somewhere and do every 7th grade. Kick ass. What system is that?
Oh.
Systematic, yeah. I'm sorry. I had a different way in mind.
I was going to say, just point somewhere and pick the closest 6.
Yeah, one way to do it is like drop your pencil onto the paper, and then wherever it hits, that's the number you pick, and then you do it again. Yes? Or you could pick every something row and then take everything in that row. What method would that be if I took every... Cluster. Do you guys understand what's happening? Or you can pick a few rows and pick some from each row. That's sort of a combination of strategy. So right now, try to randomly select 20 grades, each of you. And I'll do it too. Jeff's class, so exciting. What do you do?
Just pick numbers. Fantastic. It's the best thing I ever saw in my life.
Okay, how do I want to do it? I don't know. Don't do that. I missed where that is. There it is.
It's 57. 57.
Oh, here. Thank you. I should really watch. I don't know why I'm looking away when I do this, because I don't want to
Okay, you're right.
force it somewhere.
How many? 20 grades. Good lord.
The beauty of statistical data collection. Did I have the same thing? That was something that- Almost there.
No.
Let's get the same thing. Once you've got your 20, yeah, we can do this. All right, it's not that bad. Once you've got your 20, go ahead and put them into list 1.
Yeah, not my grade. The 49.
If you find your grade, you're not beholden to tell us what it is,
Oh, my bad.
but I don't think that's true.
I actually don't check my grades until like the end of the semester.
Well, in my class, you can't check your grades, right?
It's a superstition. Stupid.
One sheet. Wow, that sucks a lot. Oh, there, that's the one. Thank God.
Yay.
Is anyone likely to have the same sample as anyone else?
No.
Does that make sense? It's very, very unlikely that people have the same sample, yes?
Yeah.
This is what I got when I picked 20 numbers. I got a sample of mean of 76.78 and a standard deviation of 13.54. So as you get yours calculated, I want you to come up and write them on the board. And if you're not sure about what you're getting, just call me over. You can choose amongst all the various colors here.
like, why is this closed? Oh, no.
Nice.
Yeah, what table? Oh, from here?
That was a little evil. That was all good tonight.
Yeah. All,
So-
all of them are just like,
What'd you do?
Just put.
Sabrina's strong.
all in order?
She's
No,
just.
not in order, just however, because you're just gonna be getting this vote happening. Just hold that word.
One table, this one.
That's you go.
There. There.
However, like maybe mark them off as you do it. That's what I did. I did it with any class.
So after you put your stuff on the board, try to do part C. And then I'll do my part C here in a minute. Yeah, yeah, that one's a little mean.
Thank
Sure.
Wait,
Yeah, let's retire that guy. Thanks, man. Put you back there. Everybody should get the same T-score because everybody's got the same degree of freedom. And you got the same alpha, right? So if you're not sure about your T-score, you can ask somebody near you. How's everybody else doing? Yeah, okay. Sure. All right. 7, 6, 9. So I got 2 people to go, right? You doing okay over there, Nico?
Yeah, just, drink
I don't
water.
know if I
earlier.
could help out.
Drink water earlier. Just coffee.
That'll mess you up, man, if you drink some water. Let's see.
I don't know, sometimes of that.
Let's see. Yeah, there's me. Is that true? Yeah.
Oh, yeah, I don't know what's going on. I just make it-
Oh, okay, you put them in? Okay,
Yeah.
gotcha. Sure. Again, just to really make sure you understand, you're not gonna get the same answers I do. No, you're fine. Yeah.
I was making sure if we're supposed to be writing it as like the pair.
Who's the math guy? We like those intervals. Interval notation. But that works too.
Sounds.
Now I think only one of us, now again, I really want to make sure you understand this. Inherent in the problem, we are making a 90% confidence interval. What percentage of intervals will not actually catch the real mean? Anybody know? So if we're making a 90% confidence interval, what percent of intervals will not catch the real mean?
The one outside?
10%. Now, there's only 9 of us, and we've only got 7 up here, but 10% of 9 rounds up to 1. So I would expect, on average, 1 person out of a group of almost 10 to not catch the real mean. I don't know if you guys are really with me. So what I got from my interval, my confidence interval came out to be 71.54 up to 82.02. This is the actual mean of everything. So does my interval actually capture this? Yes. The only interval up here that I think that might have a chance is whoever number 6 is. So now I'm really curious what your interval is going to be.
Me?
No, I'm sorry, Ryan behind you. This is really the furthest thing with the smallest standard deviation. This has a chance to not catch the real mean. So now I'm really curious about this one. So Ryan, let me know when you got yours figured out. We got the same t-score. We got 9.057 divided by square root of 7. I'm sorry, we got 7 in the brain. 20. Yeah, okay, yeah, sweet. Okay. I'm all excited. Like, ooh, I'm getting excited about numbers. Yeah. Oh, Nico, what you got?
Let's see.
So I'm sorry, Ryan, you ended up with a little extra pressure on you. But
Yeah.
You got randomly chosen to be the. Oh, Nico, you're gonna be one also. Interesting. We'll do one thing really quick.
I'll double check. I checked just to make sure it's 20.
Got you. Okay. That's interesting. So you're also gonna be one of these. I'm sorry. I gotta wait for your everything. There we go.
Oh, thank you. And then the S is X. S.
S, yeah.
Alright.
Got a big ass standard deviation, so that's gonna make it
Harder.
well. What that's gonna do is it's gonna make the composite a little wider, so you end up with a chance to catch the real mean. Okay. Ryan, I don't mean to put pressure on you. Do you have your confidence interval? Almost. Okay. I think it's
82 or
3 point something.
Yeah, oh, yeah. 3.50.
Yeah. So 82.45
$4.48.
up to 89.45 roughly, I believe. 3.501 is on. Yeah, 3.502 really, but that's all right. Nico has a chance also. So out of 8 people, I would expect on average one of them to make an interval that doesn't catch the real mean if it's a 90%. If I did a 80% confidence interval, I would expect 20% of people to create an interval that does not catch the real mean. So this is what we mean when we say a 90% confidence. So I am 90% confident that my interval I made actually catches the real mean. And this is a concrete example of, hey, there's one that doesn't. There's always a chance that when you make this, it doesn't catch the real mean. That's why we say we're 90% confident. There's a 10% chance we're wrong, and there you go. And Ryan did nothing wrong in his calculations. I really want this to be understood. Inherent in this is a built-in, we don't know for sure. That's just the way life is. So some people discount statistics because either it doesn't give them the exact thing, or they're like, oh, I can say whatever. No, if you understand statistics, you know what to look for. People can't lie to you if you know what to look for. Okay, all right. Okay. All right, I think that's plenty for today. So the section 8.2 is where you're going to use t-scores or z. You got to pay attention to what's given to you in the problem. Thank you, guys. Thank you. Please don't forget your stuff. If you traded stuff with